Now we're going to assume a net force equal to negative kV. That would correspond, for example, to rolling a ball underwater on a level surface so that there's no force except the force of the drag of the water on the ball, so that the net force is negative k times the velocity. We start the ball off with some velocity, and we're going to immediately get a force working in the direction opposite our velocity, which is going to slow the object down and as a result decrease the net force, which decreases our velocity but not quite as fast as before, and so on. Now, if we want to do this in terms of time, then our velocity is going to be a function of time, and our F net is going to be m dv dt. And that's going to give us our equation, m dv dt equals negative kV. If, on the other hand, we want to analyze this in terms of the position of the object, get the velocity as a function of where it is, then we're going to use the form mv dv dx, and our equation is going to become mv dv dx equals negative kV. So here our dependent variable is going to be time, here our dependent variable is going to be position, and this both solutions are going to describe the motion of the object. It's just that this one will describe it in terms of time, and this will describe it in terms of position. Both equations are easily solved. We separate this equation and we get dv over v equals negative k over mt. Integrating both sides, we get the natural log of the absolute value of v equals, that's k over m dt, equals negative k over mt plus an integration constant. If v is greater than 0, greater than or equal to 0, then we end up with being able to remove the absolute value signs. Absolute value of v would just be equal to v. Exponential on both sides is going to lead us to the velocity function v of t equals e to the negative k over m t plus c, which we'll write in the form a equal to negative k over m t, with the proviso that a is greater than 0. That's our general solution for the velocity as a function of time. If we want the velocity as a function of position, we can solve this equation. This is even easier to solve. The v's divide out, and we end up with just dv equals negative k over mt. Integrating both sides, we get v equals dv is negative k over m dt. Thinking ahead, we get v equals negative k over mt plus a constant, and without going through the details, it's easy to see that that constant can be interpreted as our initial velocity. If t equals 0, then v equals c, so that our function would be v of t equals v naught minus k over m, and I've called the variable t, the variable is x. Seems that when I get in the habit of writing t over here, I continue the habit without thinking. You do have to be careful about that. Okay, so v of t is v naught minus k over m times x, and it's v of x, not t. So our velocity function is now given in terms of the position x. This solution is consistent with this solution. We could take the derivative of this velocity function and interpret that derivative in such a way as to agree with this interpretation. I'm not going to go through those details right now, but that might appear as a problem.